exercise 1.1 first question. We have to determine whether the following are reflexive, symmetric and transitive. So consider the first relation. Relation R defined in the set A equal to 1, 2, 3 up to 14. Defined as R equal to set of all ordered pair xy such that 3x minus y equal to 0. So this relation R is defined in the set A. So it is a subset of A cross A. So in the ordered pairs, first element and second element, both these are elements of the set A. That should be from the set A. And the elements will satisfy one more condition, that is 3x minus y equal to 0. That means 3x equal to y. So we can write that relation as a in the listing method. We can write roster form. We can write all the elements. See here R equal to, the relation R equal to, we can write. See here it is given in the set builder form. We can write in the roster form. So we can write all the elements of the set. So here set of all ordered pair xy such that 3x minus y equal to 0. 3x minus y equal to 0 means 3x equal to y. So all such ordered pairs we can write in this set. So in this set, in all relations, all the elements are ordered pairs. So we can write all the ordered pairs belonging to the relation R in the first question. So here y equal to 3x. That means y element. Y means second element. Second element equal to 3 into first element. And here consider 1 element belonging to A, 1. So when x equal to 1, if you take first element 1, y should be, second element is 3 into 1. So 3. 3 into 1, 3. So that is one element belonging to the relation. Then when x equal to 2, 2 into 3, 6. So 2 comma 6 is an element of this relation. And remember that this first element and second element should be element of A, set A. So now we can consider x equal to 3. When x equal to 3, y equal to 3 into 3, 9. 3, 9. Then consider x equal to 4. When x equal to 4, y equal to 4 into 3. 3 into 4, that is 12. 12 is 4 and 12. Both are elements of A. So that also we can write. Now when x equal to 5, here 5 belongs to A. So when x equal to 5, 3 into 5, 15. But 15 is not there in A. So we cannot write that element. So only these 4 elements are there. For higher elements, when x equal to 6, 3 into 6, 18. That also not there. So only these are the 4 elements of the relation. So we have written the relation, given relation R in the roster form. We write all the elements in the set. Now this is the relation. Now we have to check whether it is reflexive, symmetric and transitive. So reflexive means we know for every here in A there are 14 elements. So for corresponding to each element, since 1 belongs to A, 1 should be there in this relation. Since 2 is there, 2 should be there, 3 4 also those elements should be there in this relation. Then only we can call that reflexive. Now if it is not reflexive, we can show with only one example. Only one example is enough to show that it is not reflexive. So just to write one example where why it is not reflexive. So we can write the reason like this. 1 1 is not an element of R. See here 1 is an element of A. 1 is element of A and 1 1 does not belong to R. Therefore it is not reflexive. Therefore R is not reflexive. So that only that is enough to show that it is not reflexive. So only show with one example. So 1 belongs to A but 1 does not belong to R. Therefore R is not reflexive. Now symmetric. Why it is not? Is it symmetric? If it is not symmetric, just to show with one example. See here 1 3 is an element of R but 3 1 is not there. 3 1 is, so just to write the example. So 1 3 is an element of R but 3 1 is not an element of R. So 1 3 is an element of R but 3 1 is not there in R. Therefore we can write, therefore R is not symmetric. Therefore R is not symmetric. So just to show with one example, only one example. Now transitive. Is it transitive? If it is not transitive, write with one example, show one example. So here see, with the second element 3. 1, 3. Then 3, 9. So 1, 3 is an element of R. 3, 9. See, here second element, here first element, same. So consider such a pair of elements. So 1, 3 is there, 3, 9 is there. Then what should be there? 1, 9 should be there. 1, 9 should be there in R. But see, 1, 9 is not here. So that we can say it is not transitive. So 1, 3 belongs to R and 3, 9. 3, 9 is an element of R. But 1, 9, here first element 1, last element 9. So 1, 9 does not belong to R. Therefore, R is not transitive. So only that is enough to write. So here this relation, given relation is neither reflexive nor symmetric nor transitive. So just to show with one example. So that is why that is how we prove. Now see second question. R in the set, relation R defined in the set n of natural numbers defined as R equal to set of all ordered pair xy such that y equal to x plus 5 and x less than 4. So we have to show. Second one, here set of all ordered pair xy such that y equal to x plus 5, x less than 4. So we can write the relation in the, here only few elements are there in the relation. So it is easy to write the elements of the relation. So we can write the relation R as a, in the roster form. So write all the elements of the relation. In the set, this is defined in the set n natural numbers, set of natural numbers. So in the ordered pair, first element and second element are elements of natural numbers, set of natural numbers. So that they are natural numbers. So here in this relation, this ordered pair satisfy these conditions. Y equal to x plus 5. Y means second element. Second element is equal to first element. Second element equal to second element plus 5. One more condition, x less than 4. That is first element. First element should be less than 4. And given that it is defined in the set of natural numbers, so ordered pair, all the first and second elements are natural numbers. So we can write all such elements in the relation. So we can write the elements of the relation R. So remember, all the elements are ordered pairs. So first ordered pair we can write x less than 4. That means first element should be less than 4. So less than 4, which are the natural numbers? 1, 2, 3. Only 3 natural numbers less than 4. So consider x equal to 1. First element 1. So what is second element? Y. Y equal to x plus 5. So 1 plus 5, that is 6. Then consider x equal to 2. So 2. 2 plus 5. Y equal to x plus 5. 2 plus 5, 7. Then x equal to 3. 3 plus 5, 8. Only these elements, because x should be here given that x is less than 4. So only there are 3 natural numbers less than 4. So only the possible values of x are only 1, 2, 3. So corresponding to 1, 2, 3, we wrote the y element. That is y equal to x plus 5. So only these 3 are the elements of R. Only 3 elements are there in R, relation R. Now we have to see whether it is reflexive, symmetric, transitive. Now see here, for the relation to be reflexive, see here defined in the set of natural numbers. So here, for every element in the set of natural numbers, 1, 1 should be there in this relation. 2, 2, 3, 3. All those elements should be there in the relation. But here nothing is there. So we can show only one example. So we can write 1, 1 is not an element of the relation. But for n, for 1 belongs to n. For 1 here 1 belongs to the set of natural numbers. But 1, 1 does not belong to R. Therefore, R is not reflexive. So, not reflexive. Now, symmetric. Check whether it is symmetric. See, 1, 6 is an element of R. But 6, 1 is not here. Similarly, 2, 7 is here. 7, 2 is not there. 3, 2 is there. 8, 3 is not there. So, you have to show only one example. So, we can write 1, 6 is an element of R. But 6, 1 is not an element of R. Therefore, we can write, therefore, R is not symmetric. Therefore, R is not symmetric. Now, we see the transitive property. See, transitive here. See, there are 3 elements. See, what is transitive property? If AB belongs to R and BC belongs to R. Only if AB and BC are elements of R, then AC should be there in R. But here, see, 1, 6 is there. But with this here second element 6. And there is no other element with the first element 6. Continuation. See, transitive means AB belongs to R and BC belong to R. So only if AB and BC, see AB, BC, here second element, here first element same. Only if AB and BC are there in R, then only AC should be there. So here with the first element 6, there is no other element. Similarly, here second element 7, there is no other element with first element 7. Here 3, 8. So here second element 8, and there is no other element with first element 8. So here these two properties we wrote. Now when we write the transitive property, see we can say this relation R is not transitive. R is not transitive if AB belong to R and BC belong to R and AC does not belong to R. See, we can say this relation is not transitive if AB belongs to R and BC belongs to R. In these, AB and BC are there, but AC is not there. AB and BC are elements of R, then if AC is also in R, then we can say it is transitive. We can say it is not transitive if AB belongs to R and BC belongs to R, but AC is not an element of R, then we can say it is not transitive. But here, we do not find such a situation here. AB is an element of R and BC belongs to R and AC does not belong to R. So we can say it is transitive. Therefore, this relation is transitive. Therefore, we can write that we do not find such a situation here. We do not find such a situation here in this relation. Therefore, R is transitive. Therefore, R is transitive. So, only if AB belongs to R and BC belongs to R and AC does not belong to R, then we can say it is not transitive. So, only if these two elements are there, then only AC should be there. Here, these two elements, there is no such a situation here. Therefore, we can say it is transitive. Therefore, it is transitive relation. Now, consider the next one. R in the set A, 1, 2, 3, 4, 5, 6, x, y is divisible by x. So here, this is the relation defined in the set A, and the relation is defined as xy such that y is divisible by x. Second element is divisible by x. See here, R. The first element and second element are elements of this set 1, 2, 3, 4, 5, 6. See, we can consider the reflexive property. See, we know here x. Can you say for every if you consider any element in A, consider 1. So 1 is an element of R because y 1 is divisible by 1, 2 is divisible by 2, 3 is divisible by 3. So if you take any element in A, xx belongs to R. Since xx belongs to R, for every x belongs to A. Since x is divisible. Since x is divisible by x. So xx belongs to R for every x belongs to A, since x is divisible by x. So what we can say, for every, if you consider any element of A, 1, 2, 3, etc. 1 is an element of relation, 2, 2, 3, 3, all such elements are there in R. Therefore, for every x belongs to A, xx belongs to R, relation R, since x is divisible by x. Therefore, we can say R is reflexive. Therefore, R is reflexive. Now we will do next in the next session.